Hey guys, this is Mrs. Harbin and we are beginning Unit 6. Today we're going to take a look at 6.1 Polynomial Functions. Now this unit, we're looking at this biblical integration. We know that God provided 4 different gospel accounts in His holy word, Matthew, Mark, Luke, and John, and they provide us different insights into the same story. We've been working with linear equations and quadratic equations, and now we're moving into graphing these equations. What graphing equations do is they help us to see the written information from a different perspective. So you spent the last chapter solving quadratic equations, and you were getting these values of x, but there was no visual with them. This particular chapter, we're really going to be looking at graphing them and seeing what those equations then are giving us. What information are they providing? Our lesson objective for today is actually twofold. So first, you, the student, will graph quadratic functions of the form f of x equals ax squared plus bx plus c by plotting points, and you'll determine the vertex, the domain, the range, and the axis of symmetry. So this should look very familiar. We worked with this all last chapter when we were solving quadratic equations. Now we're going to graph these same things and we'll find this extra information about those graphs. Let's think about what the graph of each equation would look like. 3x plus 1 equals 5. If you were to solve for x and graph that, what would it look like? Well, you'd have to subtract the 1, right? And then divide both sides by 3, and you would get x equals 4 over 3. If we were to graph that, it would just be a point on a number line. We would have to draw our number line or our x-axis. Here would be our 0, here would be our 1, here would be our 2, and 4 over 3 would be somewhere right there. So it would just be a point on the number line or a point on the x-axis. What about y equals 3x plus 10? Well, here you have 2 variables, and that should look very familiar to you. That is our equation for a linear equation. And we know that by graphing it, we would get a line on a plane. So in this particular graph, our y-intercept would be 10, and our slope would be 3. And so we would have something that looks like this, because we could plug in an infinite number of values for x and get an infinite number of values for y. So that is a linear equation. F of x equals x squared. What would that look like? Well, hopefully you remember me telling you last chapter that x squared forms a shape called a parabola, and f of x, that's just function notation, which says basically y equals x squared. Our y is a function of x. Our y is determined by what our x is, and that would make a curved line on a plane, specifically a parabola. Here's a couple of terms that we need to review to make sure we're using the right vocabulary. Right? Linear, we know, means that we have one single variable, right? One variable here, and it's going to make a straight line, linear line. Quadratics, we know, make curved lines. When we have a linear math problem, and it only has the one variable, we call this a linear equation. It's just one variable. It's going to be a point on a number line. So a linear equation, we've been solving for x and then graphing a point on a number line. A linear function has f of x equals whatever. We can replace this with y equals 2x plus 1. A linear function has 2 variables and it graphs a whole line. A quadratic equation with one variable gives us 2 solutions, x equals plus or minus whatever your number is. That's what we did last chapter. Remember, I told you those are the points where it crosses the x-axis. So 2 points on the x-axis. A linear or quadratic function has 2 variables. It has y equals x squared minus 3x plus 1, or f of x equals, and that will give us multiple points so that we can graph a whole line. So an equation gives you a specific point. Remember that, an equation gives you a specific point or points, and a function helps you to draw a line. Whether it's a straight line or a curved line, it helps you plot multiple points and then connect the dots to draw a line. Now we've done quadratic equations already, so now we're turning our attention to quadratic functions. Just a quick review of what we just said. A linear equation in one variable has at most one solution. A linear function has an infinite number of ordered pair solutions. Linear equation is a point. Linear function is a line. An infinite number of ordered pair solutions that form a line. A quadratic equation with one variable has at most two real number solutions, so that was 2 points, while a quadratic function has an infinite set of ordered pair solutions that, if we connect those ordered pairs, will form a curve called a parabola. All right, now that we've reviewed the vocabulary, let's go into quadratic functions. A quadratic function is a function that can be written in the form f of x equals ax squared plus bx plus c. Remember that f of x is really just y, but we're saying that y, the value of y, depends on the value of x. So it is a function of x, but don't let that confuse you. You're really just looking for x and y coordinates. You're already familiar with this form, ax squared plus bx plus c, from the previous chapter, and you should remember that a, b, and c are real numbers, and a cannot be equal to 0. If a is equal to 0, well, 0 times x squared is 0, and that just leaves you with bx plus c, which is a linear function. So in a quadratic function, ax squared plus bx plus c are all real numbers, and a is not equal to 0. This equation is called the general form of a quadratic function. Within that general form of the quadratic function, you can see that we have 3 different terms. Remember, we can write that as f of x here. Our first term is called our quadratic term. That's because that represents x squared, x times x. That's a quadrilateral there. A linear term and a constant term. Remember that a constant is just a number. So we have those 3 terms in a quadratic function. Let's take a look at how we would graph a quadratic function. We have f of x equals x squared plus 2x minus 3. The first thing that we want to do is evaluate the function for several values. So we're going to create a chart. We're going to make a list of x's here. We'll plug them into the quadratic function here. And then we'll write our y value, or our f of x value, here. So when we plug in -4 into that function, we're going to plug in using parentheses here to protect our negatives. We get 16 minus 8 minus 3, which equals 5. So our first point on our parabola would be -4, 5. When we plug in -3, we get 9 minus 6 minus 3 equals 0. All right, try one on your own. On a piece of scrap paper or your notes, go ahead and plug in -2 and see what you get. When you plug in -2, you should get -3. What about when you plug in -1? You should get -4. So we have 4 sets of coordinates: -4, 5, -3, 0, -2, -3, and -1, -4. Let's try a few more here. Plugging in 0, we get -3. Plugging in 1, we get 0. Plugging in 2, we get 5. And we stop. All right, we want to make sure that we graph both, or we plug in both positive and negative numbers so that we can create a smooth curve. If we don't have enough coordinates, we might not realize the exact shape of the curve. So we need to make sure that we plug in several values. After we've evaluated the function at several values, we then want to plot the ordered pairs. So here are the ordered pairs that we generated on the previous slide. You can tell that if we were to connect these, it should make a nice smooth curve. So the last thing we want to do is draw the parabola. And when we connect our dots and draw the parabola, this is the nice smooth curve that we get. Now, when you look at this parabola, you can see that an axis of symmetry divides the parabola into 2 mirror image halves. If we draw a line right down the middle here, you can see that the side on the left is equal to the side on the right. Each side is a mirror image of the other. This line that we've drawn right through the middle is called the axis of symmetry. And the axis of symmetry occurs when x equals -1. The maximum or minimum value of a quadratic function occurs at the parabola's vertex. Now, this parabola is opening up, which means it has a minimum point right here at the vertex at -1, -4. That's the minimum value. The vertex is the intersection of the parabola and its axis of symmetry. So where this dotted axis of symmetry crosses the parabola, that's the intersection there, and that is called the vertex. It is a minimum point because the parabola is opening upward. All right, let's talk about this function, okay, and see what we can figure out. If f of x equals ax squared plus bx plus c, then f of 0 would just equal to c, and the parabola's y-intercept is at 0, c. I went the wrong way there. All right, so if f of 0 equals c, the parabola's intercept is at 0, c. The parabola's y-intercept. Okay, if we go back to the one that we graphed previously, you can see that when we plugged in 0, we got -3. And if you look at our graph, you can see that it crossed the y-axis at 0, -3. So that's how we find the y-intercept. And if you remember what I told you earlier, if we set our quadratic function equal to 0 and solve for x, that's how we find the two x-intercepts. When we're talking about the domain of a function, remember domain is just the possible x values. And when you look at the domain of a quadratic function, it's always the set of real numbers. If you look at that parabola on the previous page here, you can see that this right side will keep on going and going and going, and the parabola will keep getting wider and wider and wider. So the possible domain, the possible x values, is all real numbers. Now, if the vertex is at a minimum point, like the one that we saw here, at -1, -4, then the range is y is greater than that minimum point. Y is greater than that bottom y value. In this case, y would be greater than or equal to -4. If the vertex has a maximum point, what if the parabola was like this and it had a maximum point? The range would be less than that maximum point. We represent the vertex using h and k, which is just the x and y values where the vertex occurs. Quadratic functions of the form f of x equals ax squared can be quickly drawn. So let's try one. Graph f of x, g of x, and h of x. The first thing that we want to do is make a table using at least 5 values for x. So what we can do is make a table that has x here, not a very straight line, and then one that has our f of x, which is x squared, one that has our g of x, which is 2x squared, and one that has our -1/2 x squared. And we'll plug in some negative and some positive values. We could plug in a -2, -1, 0, 1, and 2. When we plug those into each of those functions, we get very quickly -2 squared is 4, 2 times -2 squared is 8, and -1/2 of -2 squared is -2. So we can go through and fill out that chart very quickly for each of those things. We then would plot the ordered pairs and draw the parabola. This is our f of x, which is just what we call a parent function for the quadratic function. There's no numbers with it. It's just kind of the basic quadratic function. We have g of x. You'll see that multiplying it by 2 actually squishes it in. And h of x. You can see multiplying it by 1/2 actually spreads it out. And the negative flips it over so that it's pointing downward.